Hey y'all, good morning, or good afternoon. Sorry I can't be there today. That's unfortunate. I really want to be there. But just due to circumstances with my kid being sick and with my wife having things going on at work she can't miss, I just can't be there today. So I'm going to do my best to get through this with y'all. You should be turning to the practice, the thermal energy calculations. You should have worked on that yesterday, but I'm just going to go through it with you. Um, So without further ado, number one says explain the relationship between temperature, energy, and motion of particles in an object. Well, temperature is a measure of the motion of particles. And how does energy relate to that? Well, particle motion is increased or decreased by applying or taking away energy. All right, so your energy is going to affect your particle motion, and your particle motion is going to affect your temperature. Just to reflect, solids, their particles are tightly vibrating. Those particles were tightly vibrating. Liquids, free but close. And gases are going to be rapid and random. Rapid. And let's put far apart. Okay. All right, so number two says, referencing the reasoning you use from number one, explain the difference between objects that feel hot and those that feel cold. Well, for objects that feel hot, that means the object's particles are moving faster. When you touch them, energy flows from the object to your hand. This increases the motion of the particles in your hand, and you get the sensation of heat. For cold, it's going to work in the opposite direction. If you touch something that has less energy, that has a lower temperature or lower particle movement than your hand, then the energy is going to get transferred from your hand to the object. This is going to give you that cold sensation. So let me write that out. So objects, let's change that. So warmer objects transfer energy to your hand, creating the warm feeling. Colder objects pull energy from your hand, creating the cold feeling. Now, this all happens because of this thing called conduction, which you already should have went over. It's when it doesn't have to be hands, it doesn't have to be specific objects. When any objects are touching, they're going to transfer energy amongst them. That's called conduction. It's usually, well, I shouldn't say that. I was going to say sometimes it's solid, sometimes it's not. But when objects are touching and they transfer energy, that's conduction. All right. Number 3 says you've been waiting for the bus and your hands become cold. When you get onto the bus and sit down, you put your hands under your legs to warm up. After a while, your hands feel warmer, but your legs feel colder. Explain this with regards to what you know about thermal energy transfer. Well, we kind of just went over this. I mean, this is just a recap in a more real life situation. So, your colder hands, your colder hands had energy transferred to them by your warmer legs. The result is that your hands being warm, that's an increase in energy. So an increase in energy, and your legs being colder because of a decrease in energy. Once again, this is conduction. All right, number 4 says, how much energy must be absorbed? So we're getting into the math here, the specific heat type math. How much energy must be absorbed by water with a mass of 0.5 kilograms in order to raise the temperature from 30 to 65 degrees Celsius? Note water has a specific heat of 4,190 joules per kilogram degree Celsius. All right, so here's our specific heat formula. This will be provided for you on the test. Q equals MC delta T. Q is the amount of heat absorbed or lost. M is mass, C is your constant for specific heat, and delta T is the change in temperature. So here, the mass of our water is 0.5 kilograms. The constant for water is 4,190 joules per kilogram degree Celsius. And the change in temperature, we went from 30 to 65. So we subtract our final minus our initial, and your change in temperature is 35 degrees Celsius. Then we just multiply. So 0.5 times 4,190 times 35 is going to be 73,325 joules, and that's your answer. Okay, this is just the amount of heat that needs to be absorbed by water. It's how much you need to heat the water up to get it to change that much temperature concerning that amount of water, that much mass of water. Something that you'll notice, all of these questions here are going to have increases in temperature. It can actually be decreased as well, and you can get a negative number for your joules. And that just means energy was taken away, the object got colder, right? Number 5 says, how much heat is needed to warm 0.052 kilograms of gold from 30 to 120 degrees Celsius? Gold has a specific heat of 136 joules per kilogram degree Celsius. Same formula. Our mass is 0.052 kilograms. The specific heat of gold is 136 joules per kilogram degree Celsius. And the change in temperature, so we went from 30 to 120. This was a positive change of 90 degrees Celsius. Okay? When we multiply all that out, you get 636.5 joules. That's how much heat it takes to warm up that much gold, 90 degrees Celsius. All right. Number 6, same situation. Nothing really different. Here your mass of your copper, this time it's copper, is 9.5 kilograms. The specific heat of copper is 390 joules per kilogram degrees Celsius, and the change in temperature is 54 degrees Celsius. All right, based on that, let's compare that to number 5. We got a much higher mass. The specific heat is higher. If the specific heat is higher, that means the temperature is going to change more easily. Okay? We're also applying less temperature. So should our number for number 6 be more or less than number 5? Well, I'll tell you this. The significance is here, the mass. The mass is huge compared to number 5. I'm guessing it's going to take a lot of joules to be able to heat this up by that amount. Especially since you've got a higher specific heat as well. So, without further ado, when you do the math, you get 200,070 joules. So significantly higher than number 5. Gold is a better conductor than copper, and water is very hard to heat up. You notice this when you look at the specific heats. So water has a high specific heat. It takes a lot of energy to heat it up. Gold and copper, much lower specific heats. All right. Finally, number 7, the challenge question. We're starting with our same formula, but it's going to change a little bit. So this time it says, if it takes 820 joules of heat to warm a sample of zinc from 0 to 50, what would be the mass of the zinc? All right, well, there it tells us what it's asking for, what would be the mass. So we're looking for mass. Before I go any further, I'm going to want to go ahead and make my equation solve for mass. Well, to do that, I need to get everything else on the other side of the equation. So I need to divide by the specific heat constant and the change in temperature. So M is going to equal your amount of heat divided by your specific heat over your change in temperature. So the mass of this zinc is going to be the specific heat of zinc, 380 joules per kilogram degrees Celsius, over the constant for specific heat. Oops, I just messed up. Made a mistake, y'all. This is actually going to go down here. This is your specific heat constant. The Q, or the amount of joules used here, is 820. And the amount that we're heating this up, the temperature change, is going to be 50 degrees Celsius, positive 50 degrees Celsius, because it's heating up, right? So how much mass of zinc do we use? When you're multiplying and dividing within the same formula, make sure you multiply first. So 380 times 50 is going to be 19,000. And your joules are 820, so 820 divided by 19,000 is 0.0432 kilograms of zinc. There's your mass. All right, y'all please email me if you have any questions about this. Start work on that front page of your packet and then jump into the quizzes that are on Google Classroom. Have a good day. Like I said, if you have any questions at all, please email me. See y'all soon.